Okay, so now I want to talk about separable differential equations. And these are differential equations that usually have an x and a y in them. They're differential equations that, if we come across them before, our only kind of means of solving them or to get an idea what the solutions would be slope fields. And in these situations, or with this technique, we can actually figure out what the original equation was. And I say equation intentionally. Lots of times what the function, or excuse me, the equation whose derivative is, for instance, xy squared, was an implicitly defined equation, not an explicit function. So let's get started. The idea here is, in this one, we want to solve dy dx equals xy squared. And we want the solution, the particular solution that goes through the point 1, 1. So what we're going to do first is, first we're going to rewrite this as dy dx equals x squared y squared. And then what we're going to do is what's called separating the variables. So we'll separate the y's and the dy to one side and the x and the dx to the other side. So I'll times both sides by dx. I'll divide both sides by y squared. I shouldn't have done this all in one step, but here we go. We end up with this, x squared dx on the right. And on the left, we have 1 over y squared dy. All right? And then what we're going to do is antiderive each side on its own. So we'll take the antiderivative of the left and the antiderivative of the right. This can be rewritten as y to the negative 2. So I guess maybe I'll rewrite that right now. So y to the negative 2 dy is equal to x squared dx. And again, so now we're ready to antiderive both sides. On each side, I add 1 to the power and divide by it. So add 1 to negative 2, divide by it, it's negative 1. So I end up with negative y to the negative 1 on the left. On the right, I'm going to have 1/3 x to the third plus c. Now, you might think, why don't I need a plus c on each side? And it turns out that if you put a c on one side and maybe a k on the other, that when you put those two constants together, you still get an arbitrary constant. That is, an arbitrary constant combined with an arbitrary constant is just a different arbitrary constant. So we can just put the c on one side and then solve for it later on. Okay? So from this point then, we're going to plug in 1, 1 and figure out what c is. So let's do that over here. So we'll plug in 1, 1. And I get this. So I have negative 1 to the negative 1 is equal to 1/3 times 1 cubed plus c. So on the left, I just have negative 1. On the right, I have 1/3 plus c. When you subtract a third from both sides, you get that c is equal to negative 1 minus a third is negative 1 1/3 or negative 4/3. So write that down. And that'll give us our c value. So finally then we can write that we have negative y to the negative 1 equals 1/3 x cubed minus 4/3. Now, sometimes the instructions will say that you can leave your answer implicit. That means that you don't need to solve explicitly for y. You don't need to get y by itself. But in this example, it's not too hard to get y by itself, so we're going to do that, and I'll show you those steps here. Let's move this up here. This is the same as negative 1 over y. And so then over here I have 1/3 x to the third power minus 4/3. And I'm going to multiply both sides by y. I'm also going to multiply both sides by 3 to get rid of the 3 in the denominator over here. So we'll clear out the fractions, essentially. So I'll times both sides by 3y. Right here on the left, I get negative 3. On the right, I'm going to get, let's see, 3 over 3 is just 1, so I'll get y times x cubed minus, and then I'll have 4y right here. Then I'm going to factor out the y. Take that out in front, and then we'll divide. So negative 3 equals y times x cubed minus 4. Divide both sides by x cubed minus 4, and we have this answer explicit. So the solution to this differential equation that goes through the point 1, 1 is y equals negative 3 divided by x cubed minus 4. And just like when you solve any differential equation, you can check your answer by differentiating it. So if I take the derivative of this, maybe with some algebraic manipulation, you should be able to get back to xy squared. Okay, let's do another separable differential equation problem here. Here, dy dx is equal to x squared divided by 1 minus y squared. The process for most of these is going to start off the same. You want to get the y's on the left-hand side and the x's on the right-hand side. So we'll start off, we'll multiply both sides by dx and both sides by 1 minus y squared. And I'll just write what that result is. You end up with 1 minus y squared dy is equal to x squared dx. All right. I should note, we want the solution through the point 0, 1. That's what y of 0 equals 1 means, so maybe you make a note of that. That means just go through the point 0, 1. All right, so here I have the differential equation. I have the variables separated. I want to antiderive now. So on the right, I'm going to get 1/3 x cubed plus c. On the left, I have 1 minus y squared. So when I antiderive 1, I'll get y. When I antiderive y squared, I'll get 1/3 y cubed. Okay, plus c. So then from here, I can go ahead and figure out what the specific solution is. In other words, I can figure out what the c value is. So I'll plug in 0, 1. All right, so x is 0 and y is 1. So I end up with this: 1 minus 1/3 times 1 cubed. That's equal to 1/3 x cubed. And that's x is 0, so times 0, plus c. So when everything shakes out here, I have c is equal to 1 minus 1/3, so 2/3. So let's write that in. Y minus 1/3 y cubed is equal to 1/3 x cubed plus 2/3. And this one we'll leave implicit. It's quite difficult to get y by itself in this one. Solve it explicitly. So this answer is okay, but we have a denominator of 3 in 3 of the terms, so I can't help but just clear that thing out. So I'll multiply both sides by 3 here. And so I end up with 3y minus y cubed is equal to x cubed plus 2. So that's my final answer. Again, leaving it implicit, meaning that I don't have y solved by itself or alone. All right, let's do another separable differential equation example here. In this one, it would be a good idea for you, if you've watched the previous examples, to pause the video or stop the video right now and try the problem and see how you do. Give it a try, and then play the video and see if you get the answer right. So let's go through and solve it. Again, with the separable differential equation situation, I'm going to try to get the y's on one side, try to get the x's on the other side. So when I do that, I'm going to end up with, I'll times both sides by 1 plus 2y squared. So the function here is y times cosine divided by 1 plus 2y squared. So I'll times both sides by 1 plus 2y squared, times both sides by dx, and I get this. 1 plus 2y squared dy is equal to y times cosine x dx. So I won't have this completely separated in one step. I'll have to do another step, which is divide both sides by y. So here now then, I get 1 over y plus 2y dy is equal to cosine x dx. Right? Now I can antiderive both sides. And what I end up with on the left is the antiderivative of 1 over y is natural log of the absolute value of y. Antiderive 2y, I get y squared. On the right, I antiderive cosine, and I get sine of x. All of that plus c. All right, and it goes through the point 0, 1. So once I have this, again, we're not worried about solving this explicitly. Not that we would have to do that right away anyway. But once I have this, I'm going to go ahead and plug in the point 0, 1. And so that'll look like this. Let's go over here so there's no space. So we'll have natural log of 1, absolute value of 1, which is just 1, plus 1 squared is equal to sine of 0 plus c. Alright, so I end up with natural log of 1 is just 0, plus 1 is 1, so I end up with 1 equals 0 plus c. In other words, c is equal to 1. Okay. And so let's write our final answer here then. Natural log of absolute value of y plus y squared equals sine of x plus 1. Okay, and that's it for that one.